In this lecture, we are going to cover three important topics which are fundamental to any multiphase flows and more so for multiphase microfluidics. The first one is interfaces, then the related is surface tension, and when we have three-phase contact lines, then we talk about wetting. So, interfaces in any multiphase system. Interface is basically a the boundary line between two phases. Now, if we look at in the framework of continuum mechanics or under the assumption of continuum, where we assume that each fluid is continuous, all the molecules we can the Knudsen number is so small that we can assume the fluid to be in continuum. So, one fluid and another fluid, the boundary between them is called an interface. So, in that sense, this can be represented by a geometric surface that can differentiate two different fluids, for example, gas and liquid, and the boundary between them is what we call interface. Now, from our day-to-day life, we can conclude that the interface between two phases is generally a curve if it is in 2D, and planar surface of 0 or negligible thickness in 3 dimensions, and this interface is considered to be smooth. So, there might be certain instances where you have the interface number of a small amplitude waves are present, but if you look at microscopically under the continuum assumption, the interface is considered to be smooth. But at the molecular level, the separation between two fluids at the molecular level, it depends on the interactions between the molecules and the Brownian diffusion. So, if you look at macroscopically, you can have a picture of an interface. So, let us say this is a droplet on a solid surface. And so, this is liquid phase and this is gas phase, and this wall is solid. So, what we have the interface between gas and liquid. This is the interface between gas and liquid. Now, if we have a molecular view of this, then what we will see is that, let us say, one fluid is represented by molecules which are filled, and another fluid is represented by the molecules which are not filled. So, that is a molecular or microscopic view of the interface. So, when we have an interface separating two different fluids, generally what happens that the molecules in the bulk, they are attracted by other molecules. So, this molecule, for example, at the center is attracted by molecules on all sides of it, and in the bulk they have a certain equilibrium. Now, these interactions can be van der Waals interactions for organic liquids, or for polar liquids like water, these interactions can be in terms of hydrogen bonds. Now, when this molecule is at the interface, then it experiences the forces from the neighboring molecules, but on the other side it does not experience any, or even if it does, then this the force is not symmetric. So there is a net surface energy. So at the interface it has interactions with the same molecules, and the interaction of, let us say, this is liquid and this is gas. So the interface, the molecules which are at the interface, they have interaction with the liquid molecules at the bottom and the gas molecules at the top. So there is an asymmetry or dissymmetry that is caused at the interface, and to take into account this asymmetry and the surface energy caused by this, we define what is called surface tension. So this take into account this molecular effect. Now this phenomena can be for any type of interface. It can be the interface between liquid and gas, it can be interface between liquid to immiscible liquids, it can be interface between solid and gas, or it can be interface between solid and liquid. But more commonly the surface tension concept or the interface and surface tension concept comes into picture for gas liquid and liquid flows. Okay. So the surface tension is, it has the units of energy per unit surface area. So it can have a unit of joule per meter square, or it can have the unit of Newton per meter of force per unit length, or generally it may be represented by millinewton per meter. It can be represented in the literature. You might see that it is represented by the symbol sigma, and in other places it is represented by the symbol gamma. So surface tension basically takes into account the surface energy or the force imbalance that is caused because of the interaction of the molecules at the interface is not symmetric. So that is taken into account in surface tension. Now if we want to make an estimate of surface tension, let us say if in the fluid the total cohesive energy per molecule is U, then at the interface, because this molecule is able to interact only with half the molecules, then the energy loss is U by 2, and if the molecular dimension is delta and the corresponding molecular surface area will be proportional to delta square. So surface tension is this energy loss because the fluid or the molecule is at the interface, the energy loss per unit area. So we can say that surface tension is about U over 2 delta square, where delta is the molecular dimension. Now surface tension, from this one can say that if U is high, then surface tension is going to be high. So the molecules or the fluids or the liquids which has large cohesive energy and small molecular dimensions, they are supposed to have higher surface tensions. For example, the highest surface tension is for liquid metals. So for example, one of the examples of liquid metals is mercury, and mercury has surface tension of 425.4 or about 500 millinewton per meter. And oil and organic liquid, they have smaller values of surface tension because for example, ethanol has surface tension value of 22.1 millinewton per meter at room temperature. For water, the surface tension is 72.8 millinewton per meter. Now it might be taken into account here that when we talk about the surface tension, the values that we represent is generally the surface tension value with the liquid and air. The value is generally not very different for any other gas. So liquid and gas surface tension value will be like this. And now the similar arguments what we have discussed for a gas and liquid system, same thing holds true for a liquid-liquid system where the two liquids are immiscible. However, the surface tension in the liquid-liquid system is generally known as or interpreted as or called interfacial tension. When the fluids are miscible, that means the molecules can diffuse from one fluid to another, and in such case interfacial tension is 0. One example is that you have fresh and salt water, then the salt molecules can diffuse from one fluid to another, and the interfacial tension in this case is 0. For solid liquid case also, the interface is the solid surface that is in contact with the liquid, that is the interface. Generally, it is not easy to measure the surface tension for the solids, but many theoretical analysis, for example, we will see Young's law later in this lecture, they use the solid surface tension for analysis. Okay. So, the surface tension, it depends on, or it changes with mainly two properties. The first one is temperature. So, if the temperature keeps increasing, as we know from thermodynamics, that at critical point there is no distinction between the two phases, gas and liquid. So, at the critical point the surface tension becomes 0. And Atavas found a relationship for surface tension or temperature dependence of surface tension. So, where sigma is surface tension, and that is equal to 1 over nu L power 2 by 3 T minus Tc, where Tc is the critical temperature and nu L is the molecular volume. Later on, Katayama and Guggenheim, they improved the relationship that was given by Atwas, and they given a relationship in the form sigma is equal to sigma star 1 minus T over Tc to the power n, where sigma star is a constant for a liquid and n is an empirical factor. This n has a value of about 11 by 9 for organic liquids. Now, it has been suggested that it can be the n can be approximately close to 1. So, the surface tension, temperature dependence of surface tension can be represented by a linear expression where sigma is equal to sigma naught plus 1 plus sigma naught into 1 plus beta into T minus T naught, where sigma naught is the surface tension at temperature T naught. So, this is a measured reference value, and from that one can calculate the surface tension at different temperatures. Okay. So, the surface tension, it decreases always with temperature. So, you might see this beta, that means is negative, and when surface tension, let us say at an interface, there is heat transfer. So, because of heat transfer there is a temperature gradient, and the temperature gradient will cause a gradient in surface tension. So, imbalance of these tangential forces, because surface tension causes a normal stress, but then if the surface tension is different at two different places at the interface, then it results in an interface, a tangential force at the interface, and the fluid from warm region, so low sigma to high sigma, a motion is established at the interface, and this motion is known as Marangoni convection. So, Marangoni convection is basically the convection of the fluid near the interface because of the gradient in surface tension, and in this case this gradient in surface tension is caused by the gradient in temperature. The fluid moves from low surface tension value to high surface tension value, and low surface tension means at high temperature. So, fluid from the warm regions, it will move to the colder regions. Okay. And this effect is propagated, this effect is at the interface, but because of the viscous effects, the motion or Marangoni convection is propagated to the bulk of the fluid. Okay. Now, another parameter or another thing that affect the value of surface tension for the fluids is the presence of surfactants. So, what is surfactant? Surfactant is it is basically what is called surface active agent. So, these surface active agents are generally long amphiphilic molecules which have a hydrophilic head and a hydrophobic tail. So, hydro means water, or in general terms it can be liquid. So, hydrophilic head, that means the head is attracted towards the liquid or water, and hydrophobic, it is not attracted or it is repelled by the water. So, these surfactants are generally added to biological sample to prevent aggregate formation or to prevent the adhesion of target molecules from adhering to the surface. And it has a number of applications where one want to change the value of surface tension or reduce the surface tension. So, the surfactants, when it is introduced in the liquid, they diffuse in the liquid and then reach at the interface, and because of their amphiphilic nature, they do not move at the interface and they are captured at the interface. So, they lower the value of the surface tension of the liquid. So, if we plot an interface, at the interface there will be the surfactants will be something like this, where the head is hydrophilic head, and these are hydrophobic tails. So, with the increase in surface concentration, when the surfactant concentration in the bulk is increased, the surfactant concentration at the interface or the surface will also increase until it reaches a critical value, which is called CMC or critical micelle concentration. So, the surfactant molecules at above this concentration, the surfactant molecules start making groups together in the bulk and form micelles. At low concentration, so if we plot the surface tension with concentration of surfactant, then it is something like this. So, as we can see, initially it decreases linearly and slowly. At initially means at low surfactant concentration, the surface tension value decreases slowly. Near CMC or near the critical concentration, when the entire interface is occupied by the surfactant molecules, the surface tension value decrease significantly, and after that because no more surfactant molecules can occupy the interface, because the interface is already saturated with it, so the surface tension value remains constant. So, like when we have temperature gradient, a Marangoni convection is observed. Similarly, a gradient in surfactant concentration also gives rise to a gradient in surface tension. So, which again gives rise to Marangoni convection, and the motion is from low surface tension value to high surface tension values. So, low surface tension values means high concentration of surfactant, and high sigma is low concentration of surfactant. So, what we have learned is about surface tension and the effect of temperature and concentration of surfactants on the value of surface tension. Now, another important point is that what is the pressure jump, or what we call Laplace law, that relates the curvature of the surface or curvature of the interface with the pressure drop across the interface. So, to understand that, first we need to understand what is curvature, and as the curvature is it can be defined as the inverse of the radius of curvature. So, curvature can be for a curve, for a two-dimensional case, and it can be for a plane or planar surface for a three-dimensional case. So, looking at the curvature for a curve, it can be generally defined by the radius of the osculating circle. So, for example, for this curve, the curve that I have drawn by a solid line, at this particular point, the osculating circle, the radius of the osculating circle is the radius of curvature, and the curvature, which we generally represent by kappa, is 1 over radius of curvature. So, the curvature is inverse of radius of curvature. If this radius is r, then kappa is equal to 1 over r. Now, osculating circle means the circle that can fit closest to the curve at the contact point. So, the radius of curvature will be different at this point and at this point, because the radius of the osculating circles will be different at these points. Okay, and the radius of curvature, it can be positive. It will be positive for convex surfaces, and it will be negative for concave surfaces. Now, coming to the curves, the curvature in mathematical form, it can be defined as in this manner. So, for a curve which is represented by in terms of two variables, function of two variables, say x and y, two coordinates in 2D, x and y. So, fxy is equal to 0 if it represents a curve. Then the curvature is defined as del dot del f over norm of del f vector. So, this is the divergence of the gradient of f, its direction, because this is the gradient of f and it is divided by the norm. So, this is basically the direction vector for the gradient of f. Its divergence is what gives us the curvature. For an explicit function where we can write y is equal to fx, the curvature is defined as d2y by dx2 divided by 1 plus dy by dx square raised to the power 3 by 2, and in many cases it can be approximated by d2yy dx2. Okay, so this will be possible when dy by dx is significantly less than 1, then we can do that. Okay, now so we have discussed the curvature for a curve. Now for a plane it becomes a more complicated concept. So if you have a plane and a vector normal to the plane, any plane that will have this normal vector will cut the plane, it will intersect this surface along a curve, and there can be number of curves, or there can be number of planes that can contain this vector. So each such curve will have its own vector, or its own curvature. So the mean curvature of a plane or of a surface is defined by the principal curvatures of this, where the principal curvatures are maximum and minimum curvatures. That means the curves which are formed by the intersection of a plane that contains this vector, the curves which have maximum and minimum curvature containing this vector, the sum of those is defined as the mean curvature. So the principal curvature, and it so happens that the principal curvatures are located in two perpendicular planes. So if for example for a sphere there are two mean curvatures and both of them are 1 over r and another is also 1 over r, because all mean curvatures, all the curvatures are same, so that is equal to 2 over r is the curvature for a sphere. On the other hand, for a cylindrical surface, the maximum radius of curvature and the minimum radius of curvature, so in one case it will be infinite and another case it will be r, where r is the radius of the cylinder. So kappa is equal to 1 over infinity plus 1 over r, so that is equal to 1 over r. So what we have learned about the curvature, that how we can calculate the curvature for a curve and the curvature for a surface. So Laplace law, it relates the pressure inside a bubble and or a droplet to the curvature. If you have done, the excess pressure inside a bubble or droplet is generally given by delta P is equal to 2 sigma over r for a spherical bubble or droplet. So let us see how we can find out this expression. Now consider a sphere or a spherical droplet which has a radius r, and the pressure inside this droplet is P0, outside pressure is P1, and now we want to extend this spherical droplet by an infinitesimal amount, so that the radius become r plus dr. And what we need to do is to calculate the work that is required for this expansion from r to r plus dr. So in such a process there are two different type of works that are being done. The one that will be equal to let us say del W for expansion, that will be equal to P dV work, because there is a change in volume. So dV, and the pressure is P1 minus P0, because it is working against this pressure. So P1 minus P0 dV, that is the work for this expansion, and then the work due to surface change in surface area, so that will be equal to sigma, where sigma is surface tension, into dA. So at the thermodynamic equilibrium, this total work is equal to 0. That means P1 minus P0 dV plus sigma dA is equal to 0. So from this we get this expression, that P0 minus P1 is equal to sigma dA by dV. Even though we have done this derivation with respect to a spherical bubble, but this can also be done for any arbitrary shape of the interface, and dA for a spherical bubble will be for because A is 4 pi r square, so dA is 8 pi r dr, and V is 4 by 3 pi r cube, and dV is equal to 4 by 3 pi into 3 r square dr. So 3 will cancel out, that dV is equal to 4 pi r square dr. So that means that excess pressure is equal to sigma dA is 8 pi r dr divided by 4 pi r square dr. So P0 minus P1 is equal to 2 sigma over r for spherical droplet. And in general, for a surface we can give sigma is equal to dA over dV, or this you can say excess pressure, or the pressure difference, or the normal stress jump that is defined at the interface, that delta P is equal to sigma. In general it is given by sigma kappa, and so the kappa is the curvature, or sigma over radius of curvature. So this law is known as Laplace law, and this tells us the normal stress jump or pressure jump across the interface for a bubble or a droplet. So it depends on the curvature kappa. So until now we have been talking about the interface between two fluids. Now if we look at the three phase, there will be three phase contact between the fluids. So you have a solid surface, and at the solid surface there can be a droplet sitting over it. Now this droplet may be sitting like this, or it may spread like a thin liquid film. So this is liquid film. Now it depends that when these two different phenomena will occur. Sometimes the droplet might be sitting as a semi-spherical or part of a spherical part of a sphere or portion of a sphere. In other cases it might be a planar liquid film. So these two different situations, when it wets it completely and makes a film, then it is called complete wetting, and when it is forming a droplet part of a sphere, then it is called partial wetting. And this depends on that if it is a completely wetted surface or partially wetted surface, it will depend on the properties of the solid surface, liquid as well as the gas surrounding it. So a liquid spreads if the energy of the system is lowered by the presence of the film. So that means that if the surface energy per unit surface area, let us say for this is sigma, this is solid surface and there is a gas surrounding it. So this is sigma Sg. Now if we have a liquid film and it wets it, then we have two different surface energies here. This is liquid, solid and gas at the top. So here we will have sigma liquid and solid plus sigma liquid and gas. So if the presence of a liquid film lowers the surface energy, then complete wetting will occur. So let us write this. If the presence of a liquid film on the solid surface lowers the total surface energy of the system, complete or total wetting would occur. If that is not the case, then only partial wetting will occur. So in case of partial wetting, sigma Sg is less than sigma Sl plus sigma Lg. Okay. So in case of partial wetting, the contact may be hydrophilic or hydrophobic. So it is called hydrophilic. Let us define contact angle first. So if we have a droplet and the angle between the solid surface and this, the interface is called theta. and it can take another kind of shape where the angle is more than 90 degree. So in this case theta is less than 90 degree, and in this case theta is greater than 90 degree. So theta is less than 90 degree, or theta is called contact angle, and if the contact angle is less than 90 degree, then it is considered to be a hydrophilic surface, and if it is more than 90 degree, and it is called hydrophobic surface. For water, the term hydro is used. For any general liquid, one can say lyophilic and lyophobic contact. Okay. Now, Young's law, which gives us the contact angle for the surface tension for different surfaces. So, let us consider a droplet which is placed on a solid surface, and the contact angle at this surface is theta. And if we define the surface tension for different interfaces, so for sigma liquid and gas, this is sigma solid and liquid, this is sigma solid and gas. So as we have seen that surface tension can be considered as force per unit length. So using the force balance, if this is we can have a coordinate system in x direction along the surface and y direction normal to it. So force balance in x direction, if we balance the forces, then we can see that sigma Sg, force per unit length, sigma Sg will be equal to sigma Sl plus sigma Lg cos theta, where theta is contact angle. So if we rewrite it, we will get cos theta is equal to sigma Sg minus sigma Sl over sigma Lg. So this law is known as Young's law, and this gives us a relationship between the contact angle and the three different surface tension values. So in summary, in today's lecture, what we have covered is basics of surface tension. First we talk about what interface is, and now we can consider the interface to be surfaces of zero thickness and smooth surfaces which delimits or which separates the two fluids. Now we also discussed that because of the different or asymmetry or dissymmetry in the molecular attractions at the interface, because at one side the fluid experiences the attraction from one kind of molecules, and on the other side of the interface it experiences attraction from different kind of molecules. So there is a asymmetry or the surface energy generated, and this is accounted for in surface tension. And this surface tension, there are two laws that we have discussed. One is Laplace law, or it is also called Young-Laplace law. So this gives us delta P is equal to sigma into kappa in general. So delta P is the excess pressure. Excess pressure means the pressure inside the liquid droplet or gas bubble minus the pressure surrounding it. That pressure difference or the normal stress difference is sigma kappa, where kappa is the curvature and sigma is surface tension. The surface tension depends on temperature and surfactant concentration. So with increase in temperature, surface tension decreases, and with increase in surfactant concentration also surface tension decreases. And if there is a gradient in surface tension at the interface, then we see a convection setting up at the interface, and this convection is known as Marangoni convection. Another law that we have discussed today is Young's law, which relates the surface tension between three different phases or surface tension for three different phases with the contact angle.